Okay, hello. This is Dr. James Yohe, Huntington, Chapter 9, Section 3. I'm trying to get this stuff done as fast as I can. And here we're going to be dealing with the model assumptions. I sent some other videos out that I didn't make, and now I'm trying to get these made. So if you needed them, they're there for you. If you can wait for me, then you'll get the videos as I can get them pumped out. I don't think I get too many more pumped out. We're getting kicked out of here. All right. The probability. Okay, here. Oh, sorry, I forgot to introduce it. Model assumptions. Okay. So when we do these ordinary least squares, there's certain assumptions that we make. And the first one, assumption number one, is on page 491 of your book. The mean of the probability distribution of E, that's the error term, that's the difference between the actual value and the predicted value using your regression from the deterministic model, as your book says earlier. The mean of the probability distribution of E is 0. That is, the average of the values of E over an infinitely long series of experiments is 0 for each setting of the independent variable x. Thus, this assumption implies that the mean value of y for any given value of x is the expected value of y, which is beta naught plus beta 1 times x. So in the limit, the expected value of y is the predicted value. Okay, that's also the predicted value. Okay, here you've got different probability distributions. The predicted value of y when x is 5 is here, but because of that error term, we get a normal distribution around that mean. So you can see this line goes straight across here. That's the mean. Okay, so these error terms are normally distributed with a mean of 0 around the predicted value. Assumption 2, the variance of the probability distribution of E, that would be the variance of this probability distribution right here, is constant for all settings of the independent variable x for our straight line model. This assumption means that the variance of E is equal to a constant sigma squared for all values of x. So it doesn't matter how big or how little x is, the variance of the error terms around x will be a constant. That is an assumption we make in the model. If it's not true, then later on we have a test for that and we have corrections for that, things we can do when that assumption is violated. But under the model, we assume that they are distributed normally around the expected value of y with a constant variance. That does not matter what the value of x is, the variance of those error terms is the same. Assumption 3, I've already mentioned it, the probability distribution of E around those means is normal. Number 4, assumption 4, the values of E associated with any two observed values of y are independent. That is, the value of the error term, okay, associated with one value of y, say here when it's 5, has no effect on the values of the error term associated with any other value of y. So the error term, say it was here, has no effect on where the error term will lie, where the error value will be when we go to y equals 10 or whatever y equals here, 100 or 500, whatever. That the value or expected value of y, the value of y, that for any two observed values of y, that the error terms are independent of each other. Okay. Now here we've got the estimation for sigma squared for a first order straight line model. That's what we're doing here. S squared, okay, is an estimate of sigma squared. Sigma squared is for forever. It's in the limit, right? When we go from negative infinity to positive infinity on this line, as we measure these error terms across the whole line, that would be sigma squared when we took the difference between the actual values and the predicted values, and then we squared those, right, and summed them up and divided them by, right, that would be in the limit. Here, We can't do that, so we have this estimate of sigma squared. We call it S squared. And that is equal to SSE, the sum of squared errors, which you did before, divided by the degrees of freedom for the error. That is n minus 1 plus the number of x variables. Okay? So we're doing a simple first order straight line model. We have to subtract 1 for the intercept because there's a constant there, and 2 for the x variable. If we had x1, x2, x3, x4, then we'd have 5 degrees of freedom, 1 for the constant and 4 for x1, x2, x3, x4. Okay, but we're only doing n minus 2. The sum of the squared errors, if you'll remember from 9.1, 9.2, is y sub I minus y hat squared. That's the sum of the squared errors. Okay, it's also equal to SSYY minus beta 1 times SSXY. Okay, so we can do it either way. All right, SSYY, which we haven't looked at yet, is y sub I minus y bar squared. That is also equal to y sub I squared minus the sum of y sub I squared. I missed my summation signs. The summation of y sub I squared minus the summation of y, that's where we add up the y column, y sub I, and then square it over n. Either way, you can get this SSY. Okay? To estimate the standard deviation of sigma, the sigma of the error term, we calculate it as follows. The standard error is equal to the square root of the variance, which we calculated up here, which is the SSE over n minus 2. And there's our SSE, there's another version of it. We refer to S as the standard error of the regression model. So S is the estimated standard error of the regression model. Okay. We will get these here. Right here we have the root mean square error. Okay. And we have the mean square error of the mean square error, MSE, here. Okay. Now, here we're using SAS to print this out. Okay. So we can do that with a hand calculation, or we can do it off of a printout. Now here we have the mean square error, MSE. Okay. All right, of 0.3667. That is the S squared term that we calculated here. Okay. Then for a SAS printout, they call the root mean square error, MSE, root MSE. That is the standard error of the estimate. Okay. This is the square root of that with some rounding errors. Okay. Now, we would know that most of our actual values would fall within plus or minus two standard deviations of the error away from the regression line. So we could take 2 times 0.60553, and we could say that roughly that most of our observations should fall within 1.22 of this regression line here. So if we went out 2 standard deviations, about 95% of our observations, the actual observed values of y, would fall plus or minus 1.22 using the y scale here, 1.22 plus or minus the mean. I mean, the mean plus or minus 1.22. So 95% of them will fall 1.22 above the mean, and 95 and between 1.2 above the mean and negative 1.25 or 1.25 below the mean, below the actual predicted value, which is also the mean. Okay. Let's go to the next slide. Okay. Interpretation of S, the estimated standard deviation of the error. Here we talked about that. We expect most of the observed values of Y to lie within 2 standard deviations, that's 2 times the standard deviation X of the mean of their respective least squares predicted values Y. Okay. So that is not all of 2.33. One thing you'll want to do is we can construct a, where's my brain going here? We can construct a confidence interval. Okay, we can construct a confidence interval. Okay. Of where those values might fall. Okay. Lost my example. Oh, and that's something we'll do in the next chapter. Whoops, I thought it was in this chapter. Okay, I'm going to cut this off. That's 9.3. I'll try and get another one, 9.4 made before I go home. Thank you so much. Bye.